So this is a continuation of this problem because I realized I forgot the last question, which was how many complete revolutions does the wheel make before coming to a stop? So I'll do this over here. So to answer the question how many revolutions, you can say theta equals theta naught plus omega naught t plus 1/2 alpha t squared, or you could use the other equation, omega squared equals omega naught squared plus 2 alpha delta theta. Either way works. We can say the initial position is 0. We have alpha, we have omega naught, which is 2. So we have that is 2 radians per second. We have alpha now, which is minus 1/25 radians per second squared. And we have the time, which in this case is 50 seconds. 50 seconds here. So if we put all of those things in, we have theta is equal to 2 radians per second times 50 seconds plus 1/2 times a minus 1/25 radians per second squared times a 50 seconds squared. So 1/2 times 25 is a 50. So this gives us theta is equal to 100 radians. Seconds cancel out. Minus 50 radians gives us a total of 50 radians. And it asked how many revolutions. So the number of revolutions would then be, so that's radians. So the number of revolutions is, we can say theta is 50 radians. And we can say there are 2 pi radians in 1 revolution. And so we take our 50 divided by 2 pi, and we get right about 8. 7.96 revolutions, if you like. All right, now I'm going to do the other problem in this setup, in this Google Doc, which was the Fizzlet problem. So the Fizzlet problem was this problem, determining the acceleration of a wheel. And I've already gotten it so that it's gone around before this bar has come to stop it. It's gone around 1 time in ½ a second. So I already know that for this problem, my omega, at least initially, is 1 revolution in ½ a second, or 2 pi radians in ½ a second, which is 4 pi radians per second. And then what I need to do is just measure the time that it stops. So again, if I go back and watch, so this bar gets put in at 1 second, and it's still going, and it stops right about there, it looks to me, right? So at about a time, so this bar got put in, so the bar got in place at t equals 1 second, and by t equals 3.3 seconds, we have the omega final is equal to 0. So to find our alpha, we can say omega equals, omega final equals omega naught plus alpha t, or the time that this happens. So the time that this happens is about 2.3 seconds. The initial omega looks like 4 pi radians per second. The final is 0, and so we just substitute this. It's basically the same problem we did before. But what we did, I want to point out, is we did this equation. This is saying omega is equal to delta theta over delta t, we can use this because, and only because, alpha is equal to 0. Because what we're really using is theta equals theta naught plus omega naught t plus 1/2 alpha t squared. But if alpha is equal to 0, we can rearrange this and say theta minus theta naught over t is equal to omega naught. We just do a little bit of algebra here, and it gets us to this equation. So this equation is only for alpha equals 0. So that's that first point before the bar comes into place. Then once the bar comes into place to slow it down, then we use new information and we say, okay, it slows down over 2.3 seconds, which is why I put a time of 2.3 seconds in here. And then I've got that, plugging this in, I get 0 is equal to 4 times. That'd be about 12.56 radians per second plus alpha. My time is 2.3 seconds. So I get an alpha in the negative direction, because it's the opposite direction, of about minus 5.5 or so radians per second squared, rounding off. And so that would be my angular acceleration for the Fizzlet problem. Here it's just a question of knowing what to measure, and we're really doing it in 2 steps. One step is when it's rotating freely. So this is omega is constant, and alpha is 0. And then over here, once the red bar gets put in place, then we have alpha is going to be slowing it down, because it's going to be slowing down because there is an alpha. Alpha is not equal to 0, and we're expecting it to be negative if we call this initial omega positive.